let's get started with our last session. The last session we will be starting by studying Joule's law of heating. When an electric current I passes through the resistor having the potential difference V between its both ends, the thermal energy of the resistor increases. The work done by the electric field during that time, that is at time equal to T, is work done is equals to potential difference into charge, where potential difference can be denoted by capital V and charge is denoted by IT. Further, work done is equals to IR into IT. From Ohm's law, we know that V can be written as IR. Further, simplifying this equation, we can write that work done can be written as I square RT. This work is converted into thermal energy due to the collisions with the lattice, also referred as the heat produced in the resistor and is denoted by capital H or capital U. What's James Prescott studied? The name of the scientist was James Prescott Joule. He studied that a resistor's heat production in a given period of time is proportional to its current squared. That is, heat is directly proportional to square of the current. That is, H is directly proportional to I square. The another thing he noted is the heat produced in a given resistor by a given current is proportional to time for which the current exists in it. That is, heat is also directly proportional to time. The third thing he studied is the heat produced in a resistor by a given current in a given time is proportional to its resistance. That is, H is also directly proportional to R, that is resistance. Conclusively, we can say that H is equals to I square RT. Now we try to understand this concept using the exercise. A resistor produces thermal energy of 500 joules in 10 seconds. When a 2 ampere current is passed, find its resistance. So we need to find the resistance of the resistor. The next part of the question asks us if the current is increased to 5 ampere. Previously it was 2 ampere. Now if the current is increased to 5 ampere, what will be the energy developed in 10 seconds? So the time limit is same, 10 seconds in both the conditions. But now the current has been increased from 2 ampere to 5 ampere. Let's get into the solutions and write the given situations first. The given conditions are as follows. Thermal energy of the resistor is given as 500 joule and we denote it by capital H. The current supplied to a resistor is 2 ampere. We denote it by I. Time for which current is supplied is 10 seconds. We denote it by small t. As from the Joule's law formula that H is equals to I square RT. Thus, putting the values to this equation, we can write 500 in the place of H, since this is the thermal energy of the resistor. I square is 2 square. R we need to find out, that is the resistance. Time limit is 10 seconds, that has been provided in the question. On solving this equation, we would get the value of resistance as 12.5 ohms. Further, the next part of the question asks us calculated resistance of the resistor R is 12.5 ohms. Current supplied to resistor I equal to 5 ampere. Time for which the current supplied is 10 seconds. The question asks us what is the heat generated if current is changed to 5 ampere. Thus, using the same formula, the Joule's heat formula states that H is equals to I square RT. Here, by putting values to this equation, we can write it as H is equals to 5 square into 12.5 into 10. Thus, solving this mathematical calculation, we get the answer as H is equals to 3125 joules. So is the answer of our question. The next thing we are going to study is Faraday's law of electrolysis. The Faraday's law states that the mass of a substance liberated at an electrode is proportional to the charge passing through the electrolyte. The same thing can be written in a mathematical manner as following. M is the mass of the substance is directly proportional to the charge Q which is flowing in the electrolyte. This can be written as M is equals to ZQ, where Z is a proportionality constant here. Also, Z is a constant for substance being liberated, also called as electrochemical equivalent. Its SI unit is kg per coulomb. If an electric current I is passed through an electrolyte for a time t, the amount of charge passed is equals to Q is equals to IT. Putting this in equation 1, we can write as M is equals to Z into IT, as we have replaced Q by IT. This was our equation 1. Thus, it became M is equals to Z into IT. Understanding this using the exercise, the question says, calculate the time required to deposit 0.9 grams of chromium when 0.6 ampere current is supplied. Consider ECE is equals to 0.00018 gram per coulomb. Thus, using the Faraday's electrolyte formula, as we know, M is equals to Z into IT, where M is given as 0.9 grams. ECE is also given in grams, therefore we don't need to change the units. It is 0.00018 and I is 0.6 ampere as mentioned in the question. We need to find out the time. Thus, simplifying this equation, we get the result of time as 8333 seconds, and if we generalize it, we can say that it is around 2.31 hours. So, the answer of the question is 2.31 hours is required to deposit 0.9 grams of chromium when 0.6 ampere of current is supplied. The next thing we are going to study is Kirchhoff's law. Kirchhoff's law is divided into two things. The first is the Junction law. The sum of all currents directed towards a point in a circuit is equal to the sum of all current directed away from the circuit. Here we can see there are 4 resistors that is causing a complete circuit. So, the Junction law states that the sum of all currents directed towards a point in a circuit, like all currents directed towards a point, the center point, let's consider a center point in a circuit, is equal to the sum of all currents directed away from the circuit. Therefore, it says that if I1 and I2 are the two currents that are pointing towards the center and I3 and I4 are the two currents directing away from the center, then the sum of I1 plus I2 would be is equals to I3 plus I4. Otherwise, the algebraic sum of all currents directed towards a point is 0. Also, it is saying that if all the currents are pointing towards the center, then the algebraic sum of all the currents would be 0. Referring to the circuit for Junction law, as I said, I1 and I2 would be equal to I3 and I4. If we mention that I1 and I2 are possessing current towards the center and I3 and I4 possessing current away from the center. This can also be understood by shifting the RHS to the LHS, that is I1 plus I2 plus negative of I3 plus negative of I4 is equals to 0, which we have studied the second point in the previous slide. This one, the algebraic sum of all currents directed towards a point is 0. The second part of Kirchhoff's law is the loop's law. The loop's law states that the algebraic sum of all the potential differences along a closed loop in a circuit is 0. To use such a rule, the basic things are kept in mind. Those are: start from any point on the loop, go along the loop either clockwise or anti-clockwise, reach at the same point after completing the whole loop. To use such a rule, we also need to consider the following points. Any potential drop encountered is taken as positive. Any potential rise encountered is taken as negative. The net sum of all these forces shall be 0. Things to be noted: it can be concluded that electrostatic force is conservative. Work done by it in a closed loop path is 0. Thus, it is mentioning that since the work done in the complete closed loop path is 0, therefore electrostatic force can be considered as conservative forces. The next thing we are going to study is about combination of resistors. Let's start with series combination. Two or more resistors are said to be in series if the same current passes through all the resistors. Like we see in the figure, two or more resistors, there are 3 resistors here, are said to be in series if the same current passes through the all resistors. Here in the circuit we see the same current passing through all the resistors. The current is I. It is passing through R1, then it is passing to R2, then it is passing through R3, and thus getting back to the battery. Consider a circuit with resistors R1, R2 and R3 connected in a series and is connected to the battery of volt V. So this is a battery of volt V. Using Kirchhoff's law, we can say that IR1 plus IR2 plus IR3 minus V is equals to 0. As we have studied Kirchhoff's law before, that the voltage can be taken as negative if there is a potential rise, and the rest things are IR1 plus IR2 plus IR3. So the equation becomes IR1 plus IR2 plus IR3 minus V is equals to 0. We write this as V on the right hand side, and taking I as common, we also take I on the right hand side, which becomes V by I is equals to R1 plus R2 plus R3. I just mentioned that V by I is equals to R equivalent. How? We have studied in an Ohm's law that V by R is equals to V by I is equals to R. Thus the equivalent resistance is R equivalent is equals to R1 plus R2 plus R3. This argument can be extended till any number of resistors in the series. Thereby, R equivalent can also be written as R1 plus R2 plus dash 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 plus Rn, where Rn is the resistance offered by the nth resistor of the circuit. The next thing we are going to learn is parallel combination. Two or more resistors are said to be connected in parallel if same potential difference exists across all the resistors. Consider a circuit with the resistors R1, R2 and R3 connected in parallel and is connected to the battery of volt V. Let's see in the circuit, there are three resistors R1, R2 and R3. They are considered to be in parallel as if the same potential difference exists across all resistors. As we can see in the circuit, same potential difference of V exists for all the resistors. Although we can also see there is the division in current I, where I1 is the current for R1, I2 is the current for R2 and I3 is the current for R3. Thus, using Kirchhoff's law, I is equals to I1 plus I2 plus I3. Let us give this equation a name as equation 1. Using Ohm's law, we can write it as I1 is equals to V by R1, I2 is equals to V by R2 and I3 is equals to V by R3. Putting these in equation 1, we can write as I is equals to, we are taking V as a common, as V would be common for all the three resistors since this is a parallel combination circuit. Therefore, taking V as common, we can write 1 upon R1 plus 1 upon R2 plus 1 upon R3. Therefore, 1 upon R equivalent can be written as 1 upon R1 plus 1 upon R2 plus 1 upon R3. Above can be extended till any number of resistors in parallel, like 1 upon R equivalent can be equal to 1 upon R1 plus 1 upon R2 plus dash 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 plus 1 upon Rn, where Rn is the resistance offered by the nth resistor of the circuit that has been attached in parallel combination. Let's try to understand both series and combination circuits using an exercise. So here's the question. Find the equivalent resistance of the circuit as shown in figure between points A and B. So we have to consider this diagram, circuit diagram. So this is point A, this is point B. We need to find out the equivalent resistance between the point A and point B. We can see a resistor of 20 ohms in the parallel combination with the resistor of 30 ohms. Also, we see that 2.5 ohms is the resistor in series with the equivalence resistors of this parallel combination. Thus, coming into the solution, resistors in parallel are 20 ohm resistor and 30 ohm resistor. Let R dash be the equivalent resistor of parallel combination. Let's say the equivalent resistor name could be as R dash, where I have already considered 1 upon R equivalence is R dash. Thus, R dash equals to 1 by 20 plus 1 by 30. We can write as 1 upon R1 plus 1 upon R2 is equals to 1 upon R equivalence is equals to R dash. I have considered this equation and we have learned this in the previous slides. Here we have seen 1 upon R equivalence is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. I have considered 1 upon R equivalence itself as an R dash. Therefore, I have directly applied the formula R dash is equals to 1 upon R1 plus 1 upon R2, and we don't have the third resistor in parallel. Therefore, 1 upon R1 plus 1 upon R2 only. Putting values to that equation, we can write R1 as 20 ohms, R2 as 30 ohms. Thus, 1 upon 20 plus 1 upon 30 can be equal to 30 into 20 divided by 30 plus 20. Let's see how it came. As we have to sum up this equation, we have to take first the LCM of 30 and 20. So better, I have directly multiplied 30 with the 20 divided by 30 plus 20, which is equals to, in the numerator we used to sum up 30 plus 20. Okay, 30 plus 20 divided by 30 into 20. That's how we used to do. Since we have to directly find the R dash, it is 30 into 20 divided by 30 plus 20, and thus giving the result 12 ohms. Further, we can see this R dash resistance is connected in series with 2.5 ohm resistor. Therefore, the calculated resistance of R dash now going to be in the series connection with 2.5 ohm. We have calculated R dash as 12 ohms. We also know that the R equivalence for the series circuit is R1 plus R2, as we have seen in the previous slides. Here we have seen R equivalent is equals to R1 plus R2 plus R3. In our case of question, we don't have R3. R1 is the equivalent resistance of the parallel combination. We have named it as R dash, and R2 is equals to the resistance that has been given in the circuit as 2.5 ohms here. Therefore, R equivalent of the complete circuit is equals to R dash plus 2.5, where R dash we have calculated 12 ohms plus 2.5 ohms. That would result in 14.5 ohms. So this would be the answer to our question. That was to find out the equivalent resistance between the point A and point B of the circuit. Now we are going to summarize the complete things that we have studied today. So this week we have started from heat. What was heat? Heat can be defined as the energy transferred from one body to another without any mechanical work involved. Next thing we have studied after heat is temperature. Temperature is the measure of hotness or coldness and can be measured in Fahrenheit, Celsius, Kelvin and Rankine cycle. As Celsius and Kelvin are the similar units, similar is the case with Fahrenheit and Rankine cycle, although all the units result in measuring temperature. The next thing we have studied is heat current will always flow from hot body to cold body. As the hot body have greater internal energy, thus the heat current will always flow from hot body to cold body. We have also studied that heat transfer can be taken place by only three types. The first type through which the heat transfer could take place is conduction, where conduction heat transfer is due to the molecular collisions. The next kind of heat transfer that could happen is due to the convection. Convection is the process of transferring heat by actual motion of heated material. That is, when the material gets heated, it itself moves to the another part of the cold body to transfer its heat. This is called the process of convection. The third type of heat transfer that could happen is the radiation, where we can say that radiation does not require any material medium for heat transfer. Further, we have learned about the electric current. Transfer of charge from one side of an area to the other causes electric current through that area. If the moving charges are positive, then current is in the direction of the motion of the charges. Similarly, the moving charges are negative, then current is in the opposite direction of the motion of charges. We have also studied that the amount of electric current flowing per unit cross-sectional area of the material is called as current density, where J is and can be equal to del I upon del S cos phi. If the cross-sectional area is in perpendicular direction, then the current density would directly be J is equals to del I upon del S. On application of electric field, positive and negative charge particles redistribute themselves closer to surface of plate. We have seen this in electrical field concept, that when an electric field is applied, which are uniformly distributed before, try to reshuffle themselves or redistribute themselves, and they get closer to the surface of the plate. This movement of particles caused drift velocity in the particles. There comes the drift velocity. The average velocity attained by a charged particle in a material due to the electric field is called drift velocity. Just now in last point we have seen when an electric field is applied, the particles redistribute themselves. During the redistribution, they attain some velocity in them. Thus, that velocity is called drift velocity, represented by Vd, that is equals to L by T, where L is the distance covered by the particles while redistributing themselves at time t. Therefore, drift velocity is equals to L by T. Further, we have also studied Ohm's law. Ohm's law states that voltage is directly proportional to current, where resistance is the proportionality constant and depends on the temperature of conductor. As we see, voltage is directly proportional to current, where resistance is the proportionality constant. Thus, V is equals to IR. Moreover, the resistance is very much dependent on the temperature of the conductor. Also, we can write R is equals to rho L by A, where rho is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area of the conductor. Here, we also have read temperature dependency of resistivity. It can be written as RT is equals to RT naught into 1 plus alpha T minus T naught. Here, the factor L by A, which has been changed due to the temperature, has been considered negligible. Thereby, RT can be directly related to RT naught into 1 plus alpha T minus T naught. Further, we have studied materials for which the resistivity suddenly becomes zero below a certain temperature are called superconductors, where the temperature at which resistivity suddenly becomes zero is the critical temperature. We also got an opportunity to learn about the batteries. A battery is a device which maintains a potential difference between its two terminals, where also EMF of the battery can be defined as the work done per unit charge. Thereby, it can be written as EMF can be written as E, work done per unit charge can be written as W by Q. W is work done, Q is the charge. Also, work done can be elaborated as FB into D, which is force into the distance covered by the charge per unit charge. Thus, the EMF of the battery can be defined as E is equals to FP into D divided by Q. Further, we got to know about Joule's law of heating as well. The Joule's law of heating can be summarized by a single formula, that is H is equals to I square RT, where I is the current, R is the resistance, and T is the time. Further, we got to know about Faraday's law of electrolysis. The mass of a substance liberated at an electrode is proportional to the charge passing through the electrolyte. This was Faraday's law of electrolysis. The next things we have learned was Kirchhoff's law, which was divided into two, the Junction law and the Loop's law. The Junction law states that the algebraic sum of all the currents directed towards a point is zero, whereas the Loop's law states that the algebraic sum of all the potential differences along a closed loop in a circuit is zero. The last things we have learned about the combination of resistors, and we got to see that there were two kinds of combinations that are possible in resistors. The first is the series combination of resistors, where we have seen R equivalent can be written as R1 plus R2 plus R3 plus dash 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 plus Rn, where Rn is the resistance offered by the nth resistor of the series combination of the resistance of the circuit. Further, at the last but not the least, we have studied the parallel combination of resistors and have concluded that 1 upon R equivalent can be equal to 1 upon R1 plus 1 upon R2 plus dash 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 to 1 upon Rn, where Rn is the resistance offered by the nth resistor of the parallel combination circuit. Here we sum up our last session of this course. I should say thank you so much.